I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic of Gunn Diode. And Gunn Diode is one of the microwave diode. It is an active device. We know the active device is the necessity in microwave engineering. The active devices are useful for either generating microwave power or they can be used to amplify the microwave signals. So, this Gunn diode in this topic is the microwave semiconductor device, and it is a Gunn oscillator. It is an active device. This microwave semiconductor device, they include microwave diode, point contact diode, varactor diode, Gunn diode, impact trapad diodes, tunnel diodes, and microwave transistor and MMIC, microwave integrated circuits. At microwave frequencies, we cannot use the conventional transistors because of these reasons. One is the length of the leads introduce significant inductance at microwave frequency. And the second reason is high internal capacitance. Third reason is high transit time of carriers through these devices. So here the transit time is nothing but electron or proton travel from one node to another node is called transit time. And in this case of diode, for example, from cathode to anode in transistor, from emitter to base, or from emitter to collector, or from source to drain. So Gunn diodes, they are generating microwave signals anywhere from 1 gigahertz up to the frequencies of possibly 100 gigahertz. This Gunn diodes are also known as transferred electron device, which is simply referred as TED, and they are also referred to as a diode. The device is not possesses a PN junction. Instead, the device uses an effect called Gunn effect, which is named after the discovery of J.B. Gunn. So, although the Gunn diode is normally used for generating RF microwave signals, the Gunn diode is also used as an amplifier in what we may know known as transferred electron amplifier, or it is TEA. So the Gunn diode can be easy to use, and they form a relatively low cost method of generating microwave RF signals, and they are often being mounted within a waveguide to form a simple resonant cavity. So the Gunn diode or transferred electron device can be termed as a diode because it consists of two electrodes like PN junction. And Gunn diodes are fabricated from a single piece of N-type semiconductor. The most common materials are gallium arsenide, that is GaAs, and indium phosphide INP. So the device is simply an N-type bar with N plus contacts. It is that is more electron contacts. It is necessary to use N-type material because the transferred electron effect is only applicable to electrons and not holes found in the P-type material. The central region of Gunn diode is called as active region, which is properly doped N-type gallium arsenide and epitaxial layer with a thickness around 8 to 10 micrometers. So the diode is a negative differential resistance device which is frequently used as low power oscillator to generate microwaves, and it consists of only N-type semiconductor in which electrons are the majority charge carriers to generate short radio waves such as microwaves, and it utilizes Gunn effect. So in the diagram, the Gunn diagram is consists of the middle layer active layer with the N-doped semiconductors, and the two ends are N plus layers. And the diode symbol, it is like two triangles shaped one to one meet together. And if we see the characteristics, the Gunn diode operation depends on the fact that it has a voltage controlled negative resistance, and this being dependent upon the fact that when a voltage is placed across the device, most of the voltage appear across the linear active region, and this inner region is particularly very thin, and this means that the voltage gradient that exists this region is exactly high. So this device exhibits the negative resistance region on the voltage I characteristics curve. This negative resistance area enables the Gunn diode to amplify the signals, enabling it to be used in amplifiers or oscillators. So however, it is the Gunn diode oscillators are most commonly used. So as the field increases, the electron drift velocity in gallium arsenide reaches a peak and then decreases. So in the diagram it is shown, it is called as negative resistance characteristics. As the electric field increases, the energy of the electron also increases, and the electron can be scattered into the upper valley where the density of the state's effective mass is 0.55 m0. So now we are going to see the Gunn effect. So J.B. Gunn, the scientist, discovered the Gunn effect in February 1962. He observed random noise-like oscillations when biasing N-type gallium arsenide samples above a certain threshold. He also found that the resistance of the samples dropped at even higher biasing conditions, indicating a region of negative differential resistance. So this is the base for Gunn diode. This is called as Gunn effect. So by using this Gunn effect principle, the Gunn diode is working. So materials which have the Gunn effect, such as gallium arsenide, indium phosphide, gallium nitride, must be direct band gap material that have more than one valley in the conduction band, and the effective mass and the density of the states in the upper valley are much higher than the main valley. So Gunn effect is very important to note that the sample had to be biased in the NDR region to produce the Gunn diode. Once a domain has formed, the electric field in the rest of the sample falls below the NDR region and will therefore inhibit the formation of a second Gunn domain. As soon as the domain is observed by the anode contact region, the average electric field in the sample rises and domain formation can again take place. So the successive formation and drift of Gunn domains through the sample leads to accurate current oscillations observed at the contacts. So in this mode of operation called the Gunn mode, the frequency of the oscillation is dictated primarily by the distance the domains have to travel before being annihilated at the anode. So this is roughly the length of the active region of the sample L. So in Gunn oscillators, the Gunn diode will be placed at a resonant cavity. So a Gunn oscillator is comprised of two major components. One is called a DC bias circuit and another one is called a tuning circuit to tune to particular frequency for producing oscillations. So property of the Gunn diode along with its timing properties, because it to behave as an oscillator provided an optimum value of current when it flows through it. So this is because the negative resistance property of the device null if as the effect of any real resistance existing in the circuit. So this results in the generation of sustained oscillations till the DC bias is present while preventing the growth of oscillations. Furthermore, the amplitude of the resultant oscillations will be limited by the limits of negative resistance reaching. So in the diagram of Gunn diode oscillator, we have a tuning circuit, and for Gunn oscillators, the oscillation frequency depends upon the middle layer called as active layer. So the resonant frequency can be tuned externally either by mechanical or by of electric means. So applications of this Gunn diode, it is used as microwave low power oscillator, and also used in radar transmitter, pulsed Gunn diode oscillator in transponders for air traffic control, low and medium power oscillators of microwave receivers. And next is Gunn diodes can be built using semiconductors with very high electron mobility and frequency response. Terahertz oscillations have been built using this technology. Next is gallium arsenide, gallium nitride. Semiconductors are commonly used to make Gunn diodes to operate into the gigahertz to terahertz region. So this Gunn diode oscillators are known for being able to produce extremely high energy levels at higher frequencies. Hence their common use in microwave, millimeter wave and terahertz systems. So these are the applications of Gunn diode assessment. So first question, gallium arsenide is used in the fabrication of Gunn diode because the answer D, less forbidden energy gap. When the electric field applied to gallium arsenide specimen is less than the threshold electric field, the current in the material increases linearly. Thank you.